So it is time to skip ahead into Chapter 6. Chapter 6 is where we're going to look at electricity and begin with specifically electric charge and static electricity. And in order to begin with a basic understanding of that is that we have to understand that there is an atom in everything around. So everything around us is made up of atoms. Atoms is the smallest known particles in our universe. It doesn't matter what element we're looking at. It doesn't matter if it's a solid, a liquid, a gas. It doesn't matter if it's an abiotic versus abiotic factor. Everything around us is made up of atoms. Now, when you and I talked about the living versus the non-living, the biotic versus the abiotic organisms, we talked about living things having the smallest level of organization being the cell. Well, inside the cell, we saw that there were many different types of particles, like we have the nucleus and the mitochondria and the ribosomes. So we need to understand that all of those organelles, those smaller pieces inside the cells, are all made up of hundreds of thousands, if not millions, of atoms. They are that small. So when we start looking at atoms, then they are all around us, and we need to understand those as well. And there is a direct connection between an atom and what static electricity is, what electrical charge is, and what electricity is that we'll get into later. So when we start looking at the electric charges of an atom, then we have to understand that inside the center of the atom is a nucleus. Just like the word nucleus inside of a cell, where you have your DNA and all of your control parts of the cell, inside of the nucleus, that's the center of the nucleus. And inside that nucleus, we have a couple of different types of particles. Those particles being the protons and the neutrons. So when I start looking at neutrons and what they do, they are neutrally charged particles inside of an atom. You're only going to find a neutron inside the nucleus of an atom. Connected to those, I'm going to have the same number of protons, and protons are positive. So if I can remember that protons are positive, neutrons are neutral, they go together, they're inside the nucleus. I have an even amount of protons and neutrons connected together to make up my nucleus, my centerpiece of my atom. Then the third one is on the outside, and they have their own little orbits that they'll go around the nucleus. And those are called electrons. Those are negative charged particles. And because they are positive charge on the center and negative charge on the outside, then they're constantly in this battle and causing this motion to go around the nucleus. So normally you will see an atom drawn kind of like this, right? So atoms show that we have these weird ovals and stuff. Well, what they're trying to show you is that inside is your protons and neutrons, and on the outside are all of these electrons that are in motion. They're in their constant orbit where they are flying around the nuclei of the particular atom. And every single one of them has their own path that they go on, and kind of like the planets going around the center of our solar system, which is the sun, they don't run into each other. So as they're flying around, then we go from trying to see a two-dimensional shape to realizing that there are many different electrons going around the nuclei, and the orbits go in all sorts of different directions in these constant ovals as they orbit the nucleus. So as we're seeing all of these particles flying around and we have motion, then that creates this charge for each of the atoms. So when we talk about electric charges, then we talk about having some atoms are positive charge because they have higher positive attraction. Now, when we talk about things that are the same sign, so two positive objects, then they have a tendency to repel each other. They push each other apart. If I had two negative charged particles, so they have a higher negative count, those also are going to push each other apart because they are the same signs. Once again, that's called being repelled. But if my electric charges are opposites, and if you've heard that saying, opposites attract, that's going to be true when it comes to our atoms. If I have a positive atom and a negative atom, they're going to be attracted to one another. So they're going to so with the understanding that we have atoms all around us at all times, then we have to have this understanding that we have these positive and negative and neutral particles floating around us at all times as well. And therefore, we have what is called electric fields around us. Now, what the book tells us about electric fields is that it's the electric force that is exerted upon other objects. So, the electric force being the positive or negative of an atom, and instead of being exerted on, I find that to be more confusing. I talk about it being applied to. So, when we apply those electric charges, then we have these natural reactions that are happening in these electric fields. So let's give you a visual. So if I take two positive atoms, or if I take two negative atoms, notice on the left and right for the positive and the negative, what's happening to those electric fields. The electric fields are the lines coming out from the atoms themselves. So if they are like particles, then they are going to repel one another. Those lines are going to diverge from one another. They're going to bend from one another. Now, that still might be difficult for us to understand because, we can't see our atoms. But I'm sure that you all have life experiences where you can prove that these invisible fields actually are there. Have you ever played with magnets? Have you taken a magnet with another magnet, try to push the two north ends together, or try to push the two south ends together? So in the same way that magnets, when they have like poles, north to north or south to south, they repel one against, they push each other away. You can't force them together. Those magnetic fields are going to diverge. They're going to bend away from one another and cause that repulsion that's going to happen. So in the same way that those magnetic fields, when you're playing with magnets, are invisible, so are the electric fields of atoms, but they're still there. If I'm talking about the opposite, then, if I have one positive and one negative, just like with magnets, and I flip it to where I have a north versus a south, then they're going to come together, right? So when they come together, those fields are still invisible and then they connect. The same thing happens with atoms. When I have a positive atom and a negative atom, they're going to be attracted to one another. Those lines are going to converge or they're going to come together and stick to one another. Now, if you haven't played with magnets or if you're just interested, then on Canvas, I'm going to put a link to this particular video because it's like a minute and a half. It's pretty short, but it's going to show you a demonstration of him just playing with magnets and showing you between straight magnets and horseshoe magnets how same poles are going to repel. And if I have opposite poles, north and south, they're going to attract. So you're more than welcome to watch that video at this moment. So as we look at these electric fields, we understand that they're the ones that have the force of either repulsion or attraction. It's those electric fields that we can't see that we need to look at when it comes to how much force there is in the attraction between the atoms. When there's a bigger distance between the atoms, sometimes they're too far apart to even be attracted at all. But it takes a movement of these particles to get closer together for that attraction to happen. In the same way that on the video with the magnets, he was having two different magnets. And when he first started out, they were too far apart. So the attraction between the magnets, even though you had a north facing a south, then it was too weak to attract them and pull them together. He had to physically grab the one magnet and move it closer together before the one on the left even came to it. When it came to it, it was because the magnets got close enough for those fields, those electric magnetic fields, to come and pull them together. So when I have a positive and a negative atom being attracted to one another, those fields are too weak until I get them close together. When they are close enough together, then they're going to become a stronger attraction and they're going to pull stronger together. So with everything around us, every common day item, and even the air is made up of atoms, then we know that there are positive and negative charges flowing all around us. And we would expect to feel all of this electricity with these particles being attracted to one another. but we don't. And the reason that is because almost everything around us is neutrally charged. It has a zero charge to it because it's already been balanced. The positives that are floating around there have met up with the negatives. They've attracted to one another, and they're stuck together. However, not everything is neutrally charged, and sometimes the charges change because electrons and protons will build up on items. For instance, maybe you've noticed in your home, like I do here at Granville Wells, that the metal around here has some electrons building up. So what's happening is we don't have a lot of moisture in the air. The humidity in the air, the moisture in the air has a positive charge. So we have all these electrons, these negative charges building up on metal because metal is one of those things that they are automatically pulled to. In the same way, if I look at wool socks on carpet, I'm sure some of you have experienced this, if not all of you. If you rub your feet back together on the carpet, you're going to be building up positive charges in the same way that the person with the balloon on the introductory video to this lesson started rubbing their head with the balloon and their hair was able to stand up and they're able to pick up papers. It's because they were building up positive charges when they were rubbing the hair and the balloon together. Well, what ends up happening then is when we have this static electricity happening, we have these particles building up on us because we've rubbed our feet with our wool socks on the carpet, coming in contact with the particles that build up on the inside of our doors and with the metal handles. And so we have all these negatives and positives. And when they come close together, then we have this static. So when we talk about static electricity, then we have to talk about some specific vocabulary words. So on these last couple pages in your book, you'll see that we have friction, conduction, repulsion, induction, and polarization. A lot of shun science. So with those electric charges then and being able to change them or increase them or exchange them or move them. So we have those terms that we need to look at. So friction is exactly what it sounds like. So we've talked about friction. We talked about rubbing friction when we rub our hands together and increase the heat inside of our hands. Well, when I rub objects together, I can build up static electricity. On the introductory video the day before then, it showed how if I rub my head and a balloon together, I get a reaction in the same way this little baby, its hair is being attracted to the balloon. The same thing would happen to us. On this video that you see in this image, which I think you'll have to go to if you to the actual PowerPoint or the individual posting that I have for you on Canvas to watch the video, but he does the same type of example where he rubs the balloon on his head and talks about that attraction and those particles sticking together. Conduction then is when I can build charges from one object to another. So when I look at this particular example, he has this in the video image that you're looking at, but this is called an electrostatic generator. So it is a machine that when I plug it in, it will begin to build charges. If you and I put our hands on it, then it's going to cause different things like our hair standing up, just like this little guy in this picture. In the video, you'll see that he has a metal wand and he's going to show the exchange of static electricity particles when he moves the metal wand close to the generator itself. Then there's another video that I'll have for you. I believe the image is on the last slide, but it talks about induction. And induction is when I'm going to cause an increase of particles to move from one side to the other. So on this example A, you can see where the particles are spread out evenly between positive and negative, but I can do something to cause them to separate from one another. So when I take this particular image, he's using a PVC pipe and aluminum can, and he has rubbed one side of the PVC pipe with wool. And that caused this induction, the shift of positive and negative to where negative is on one side, positive is on the other. And then when he moved it towards the aluminum can, it caused it to begin to roll and turn away. And it went right down the table. You'll have access to that video as well. Polarization then is a reaction to the charged objects that we have. So polarization, when I have that buildup of static electricity, that's when you can pick up pieces of paper or other things with a balloon that you have rubbed on your head or with some wool. One more thought on the idea of induction, the buildup of positive and negative charges. That's what happens in storm clouds when you have that giant exchange of static electricity that we know as lightning. So when I look at the polarization, then I am able to see how I have this reaction, what's going on when I have these different particles that are attracted to different objects. Okay? Now, once again, when I look at the idea between friction and conduction versus induction and polarization, friction and induction is exchanging particle attractions. However, when it comes to induction polarization, I'm not exchanging charges. There's not going to be any kind of exchange. There's not going to be a snap with a static electricity, right? They're just showing that there's going to be kind of like magnets, an attraction that's happening with those two. So why don't we have static electricity reaction at all times? Well, once again, most things have no charge around us. The exchange has already been happened and they've become neutral, so there's not a high positive or high negative. So if they're just neutral, we don't have to worry about these static electricity charges happening all the time. Unlike lightning. Lightning is where there's a huge exchange that's going to happen. Lightning is static electricity. It is a lot of positive charges here on the earth. Our ground is naturally a positive charge. But when it comes to clouds, they become polarized, especially the more violent storms become. So in the top, particles become heavy up at the very top are positive, where the bottom part of the clouds become heavy, condensed, negative. And when I have all these really high amounts of negative charges in the bottom of the clouds and all of these positive charges on the ground, then when the cloud gets low enough, we have the static electricity that's going to happen, right? So all of this lightning can happen, and lightning can go in three different directions. Most of the time, we think the lightning just comes from the sky and hits the ground, and that's not true. So we can have lightning that goes from the ground up into the clouds. In the same way, we can have lightning that goes from the clouds down to the ground. And then the third way is we could have lightning that happens both from the top and the bottom and they connect together, right? So when I hear that big pop, that's, what we call the, sound of lightning, but that is the static electricity being exchanged between the positive and the negative. Once again, our ground is always a positive charge, where up in the sky, the heavier those clouds become, the negatives sink to the bottom, the positives rise to the top, and therefore that static electricity is attracted to one another. And that's where lightning comes from. So when I start looking at that static electricity, it's the exact same kind as when I rub my socks on the carpet and I go and touch something metal or maybe the back of somebody's ear to give them a shock. It's the exact same thing. But that static electricity, when I touch somebody's ear, just kind of startles them, maybe hurts a little bit, but it's not deadly. Where the charges from the earth and the clouds becomes quite deadly because we're talking a lot of volts of electricity. All right, so that is the end of this recorded lesson. So I will put a link to this particular video also. So this deals a little bit more with the induction and polarization in his examples that he's talking about. And then there's also an image of the electrostatic generator with a little bit more hair reaction than the little blonde boy. But your next thing is to do the assignment, and please do it and have it turned in by the due date.